Good morning, good afternoon, and good evening. My name is Maureen Price, and I will be the moderator for our presentation today. I am the leader for Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success, and this webinar series is an opportunity to showcase specific expertise or to talk about new trends or even code changes. As with the other webinars, this will be a technical presentation intended for anyone who is interested in learning about the 30 years of industry-leading innovations in delayed coking operation. We have two subject matter experts with us today. I'll introduce Kevin Chase first. Kevin is Fluor's Director of Construction and Fabrication in the Americas. He has more than 30 years of experience in engineering, construction, and maintenance. Through his career, he has worked in project and construction management, quality assurance, and in engineering inspection. Kevin has worked on numerous coker projects as a project construction specialist. Kevin's spare time is currently dedicated to his wife and his 4 children, and he thrives while supporting them in their academic and athletic endeavors. Joining Kevin is Grant Anderson. Grant is a process engineering director with over 30 years of process engineering design and leadership experience at Fluor. Grant is a recognized subject matter expert in delayed coking and has spent more than 10 years working directly on delayed coking projects, including off-site and utility design considerations, as well as projects centered around NOx reduction, clean fuels, and renewable energy. When not geeking out on the topic of delayed cokers, Grant enjoys the outdoors, traveling, and spending time with his children and grandchildren. I'll ask Grant to unmute his line to share a brief safety topic and then begin.
All right. Good morning, everyone. Thank you, Maureen, for the introduction. So I'm going to show 3 photos that will show the evolution of unheading systems and how unheading has changed in delayed coking. The changes over the last 30 years have greatly enhanced safety and have removed operations from tasks that put them at risk. So the first photo on the left shows how operations had to manually remove a bottom head or blind from the bottom of the coke drum. They would have to pull 30 or 40 nuts with a pneumatic wrench. You can see the blind near the operator's shoulder with all those nuts. And you can't see his wrench, but he's got an air hose behind him connected up. All this is being done near a hot coke drum up on a small platform. And then the operator never knows what contents will spill out once containment is broken, right? So at some point, that blind's going to drop down just a little bit, break containment, and coke could fall out, hot water could fall out, steam could come out of the coke drum. So this is how it had been done for many, many, many years. The second photo on the right shows an unheading device that drops down and swings away. In this sense, and you can't really see the blind, but in this installation, the blind is hinged and is lowered with a hydraulic mechanism. The actuation is done remotely away from the bottom of the drum itself, enhancing safety. So there's a local control panel 50 feet away. They push a button, it unclips. You push a button, and then the hydraulic mechanism swings the blind out of the way. The chute still has to be lifted up after the head is swung away. The third photo shows a fully automated coke deheading system. The unheading device here is a slide valve, which is bolted up to the bottom flange of the coke drum. The valve moves or slides laterally out of the way rather than swinging down and away. This then allows the chute to be in position all the time. And there's so many accessories here, it's kind of hard to see everything. But Kevin will show a slide showing what a slide valve looks like later in the presentation. This system is fully remotely operated. Operations doesn't need to be there except maybe to ensure the slide valve is moving on demand. Any material spillage goes directly into the chute, directing it to storage below. The point of sharing this evolution and design is that safety and design can come from many sources: designers, operations, management, maintenance. It can be from the refiners, contractors, vendors, licensors. It just takes someone to say, what if? What if we do something to make this better and make it safer? Enhanced safety can originate from anyone willing to look at things differently and take initiative. So now I recognize that not all the participants in this webinar have a working knowledge of delayed coking. So I thought I would spend just a little bit of time, a few minutes, to introduce delayed coking with the hope that will help as we present other ideas later in the presentation. This schematic here shows the basic working equipment in a delayed coker. There's fractionation, charge pumps, a coker furnace, coke drums, always in pairs, and decoking equipment. It's actually way more complex than this, especially when it comes to instrumentation and safety systems. So delayed coking is a severe thermal cracking process which breaks very long chain hydrocarbon molecules, such as tar, into smaller molecules, such as off-gas propane, butane, naphtha, diesel, and gas oil. This is done by adding large amounts of energy via the coker furnace with effluent temperatures over 900 degrees Fahrenheit. It converts essentially unusable, low-demand material into higher-demand, useful intermediates and products. The off-product or byproduct of this process is the production of petroleum coke, which is essentially 85% carbon with other impurities. Other byproducts of the reactions are the formation of ammonia and H2S. So the cracked usable products leave the coke drum as vapor and are sent to the fractionator for further refinement. The coke drum, the coke remains actually in the coke drum and eventually has to be removed once the coke drum is filled with coke. Note that the coke drums are located in a structure generally 50 to 100 feet above grade, and the coke drum size is dependent upon throughput, but sizes of 17-foot to 32-foot are common, and the overall height of a coke drum is about 120 feet. So at the start of a coking cycle, here I have a schematic showing basically one drum that's empty and one drum that's full. So the one drum is empty and ready for the process to be diverted once the first drum is filled with coke. The entire process from feed to furnace through an on-stream coke drum with products routed to the fractionator is a completely continuous process. At this point, after switching, both drums remain pressurized and the drum full of coke will work through its way through what's called a decoking process. The decoking process of a drum that is filled with coke requires cooling of the coke drum, removing of the coke drum's heads at the top and bottom of the drum, and then removal of the coke can be accomplished. This next schematic here shows kind of what would be kind of mid-cycle as the one drum has been filling up with producing products and filling up with coke. In the off-stream drum, the heads have been removed and coke is being cut out of the drum with a high-pressure water stream as a cutting mechanism. Both the top and bottom heads require removal as a drilling mechanism is lowered through the top head and coke falls through the open bottom head to a storage or transport facility. Opening the drums to cut coke happens once a day for a single pair of drums. So for a plant with 4, 6, or 8 drums, operations is removing the heads and cutting coke multiple times a day. So as the one after the mid-cycle, as I'm continue on and I'm starting to fill the on-stream drum, I'm still going through the decoking cycle. On the off-stream drum, I've cut the coke out of it, and now we can rehead that drum and go through a warm-up stage to make it ready to be placed in standby mode. And then once the on-stream drum is filled with coke, we'll switch over to the standby coke drum. So the decoking operations have traditionally required activities that are dangerous and put operations personnel in harm's way, as I pointed out in discussing the safety topic earlier. Because of this, most of the innovation in recent years in delayed cokers have to do with increasing safety, though some developments have helped increase efficiency and reliability of plant and equipment. So for instance, I described the unheading devices. There's been advancements in coke cutting tools. instrumentation around the coke drums, including level devices and interlock permissive systems, and product filtration downstream of the fractionator. And Fluor has been part of this innovation for over 30 years. So in the last 30 years, Fluor's performed 80 projects, both design and construction projects. They've been both grassroots and revamp projects. Okay. We've done 9 grassroots DCUs over the last 30 years. We've done 44 drum replacements as revamp projects. Of note, Fluor has 14 coke drum deheading system and delayed coking patents. And we've been an innovative leader in the industry for quite a while. With both the DCU patents and the innovation, I'd like to recognize just a few of the excellent mechanical engineers instrumental in forward thinking and innovation that I've worked with in the last 30 years. So we have very good mechanical engineers. Les Dalfi and Mike Knowles were both instrumental with respect to Fluor patents and innovation. Kenneth Kirkpatrick is an expert in finite element analysis, and I'll explain that in just a second. And in my office, I've worked directly with Mark Thies and Pat Lawley. They're my local office experts with regards to coke drums and unheading devices. So just kind of looking at a timeline of coker work that Fluor has done. We've done innovations way back for 30 years now. First coker ball switch valve, first coke drum unheading system. 25 years ago, we started using this finite element analysis to extend coke drum life. We've been a player in all kinds of unheading system devices on coke drums. We came up with a removable drum insulation concept to be able to inspect drum weld seams. As of 20 years ago, we put in the first totally automated top unheading system. And then in 2001, we participated with Delta Valve in installing their first slide valve. And we've been doing that for 20 years with them now. And more recently, we've developed a trolley support system for the Delta valves. And we've looked at optimization of flow rates and quench rates to maximize drum life. And all that has to do with this finite element analysis that I'd like to explain now. So what is finite element analysis? So finite element analysis is an intelligent and computerized method for forecasting how an engineering component will react to real world forces like vibration and heat. It predicts whether a component will fail, collapse, wear out, or work the way it was designed. Because coke drums are subjected to repeated thermal cycling at approximately 18 to 24-hour intervals, these vessels almost invariably develop bulges. With the proper inputs, FEA analysis can estimate how much deformation is acceptable before the vessel should be taken out of service or repaired. So it's very common for this analysis to be performed for the skirt to shell cone junction, as shown in this schematic. Since the drums are in cyclic service, this is the most critical point on a coke drum. The operation curve determines the severity of the thermal gradient in this area. And many of the old failures on old coke drums, such as buckled plates and cracked weld seams, have not appeared on newer coke drums due to this analysis by matching plate yields, grinding inside and outside of weld seams, and having a constant thickness of drum plate material. So Fluor has done many of these analysis on coke drums, and I mentioned that Kenneth is our expert in running these analysis, and he's authored many papers on this specific topic. So very, very interesting series of events that have happened over 30 years in delayed coking. So I'm going to hand it over now to Kevin to talk about some interesting construction considerations for these types of installations.
Grant, thank you. Maureen, thank you for the introduction. And I'd like to thank everybody for joining us today. So in the next few slides, I want to talk about some of the challenges, some project highlights, and then give you just a brief overview on some of the equipment and deheading devices that we install on the revamp project. So some of the challenges that are faced in a coker replacement project is evaluation of the existing structure. All of these revamp projects are done in an existing structure. Those structures are older, so they pose a lot of challenges to us, whether that's an alteration or repair, and then also the addition of new equipment or steel, so we have to do verification of loads and such on the existing structure. And then, of course, we're trying to provide a very good design that meets our client's requirements and provide a low-cost option as well to our client. Some of the other challenges are local building codes and local municipalities, whether that's on a west coast or if it's in a location that doesn't have a high seismic zone. We have to work hand in hand with the building department to meet all the local regulations and codes. And sometimes those pose challenges determining exactly what our amount of additions will be to the structure to handle the new loads. And then also we have short turnaround time space. So these projects are all done in existing units that are in operation, and we have to work around that time frame and then work towards a turnaround or an outage when the client does shut down the unit and we can finish the project. So there's limitations in the amount of piping, the line sizes, where we can run things, pressure limits, and so on. And then logistics. So I'm going to run through some pictures, but you'll see some pictures of us transporting drums to a job site. But logistics is a very big part of this, and it has its own challenges. The equipment is usually large and heavy, and so that transfers into a little project of its own in moving the equipment to the job site. So I'd like to talk about a coke drum reliability project and some of the highlights. In the next few slides, you'll see some pictures that I'll narrate too. But some of the highlights of this project, it's a 6-drum coker. You can see the picture there on the left. It incorporated seismic upgrades to the structure. And then we had to develop quite an extensive lifting plan because the top drilling section or drilling derricks of that structure were completely removed in one piece, set on the ground, and then the old drums were removed and new drums placed, and the derrick structure put back on top of it, all during a turnaround. And this project was in 2014. So as you can see, that is the existing structure. That structure was built in 1960s, and there was, as I stated, significant upgrades to the structural portions of the unit there itself. And the next pictures are the coke drums. Those are 2 of the 6 drums being transported. The drums were originally produced in Spain and then transported to the West Coast, and then they were transported via barge to a smaller harbor that allowed us to take them off barge via SPMTs and travel to the actual job site. So some of the challenges I just briefly touched on, moving the equipment to the job site. So you got to think of this as its own project, and it has all of its own nuances. So to do this, usually we are traveling on public roadways, so there is a lot of logistical expertise that comes into play, and that's working with the local law enforcement, local municipalities, and trying to find the simplest but yet safest route to the project. So you can see the drums there on the semi-truck being moved to the project site itself. This next picture is as we're getting to the job site, there's a lot of things that have to take place. So working with the local municipalities, as I mentioned, we have to remove or modify power lines, communication lines, a lot of times street lights and signals, traffic signals come down. And then also we're diverting traffic as well as we move some of this large equipment to job sites. This picture I really like. This is a great shot of the top drilling derrick on this project being removed, set on the ground. The next step was then removing all of the older drums and replacing them. One of the neat nuances of this picture, that crane there has a lifting capacity of just over 3 million pounds, which our lift itself was just at 1 million pounds, but it was a very large crane. Took a lot of time to erect and get ready for the project. So next, I'd like to just talk a little bit about the existing structures. I've touched on it a little bit, but a lot of the structures, as I stated in the revamp, are older structures. And some of the questions that we're posed with is, one, can the structure be utilized for the project? And then what are the structural options that we have to do to make it feasible to use it for the project? And then are we in compliance with the code? As you can see on the bottom right there where the orange arrow is pointing, just as an example on that picture there of that project, an enormous amount of structural upgrades had to be done to the structure. Those are W24 I-beams that were bolted to the columns on the bottom there. You can't see all of the work actually, but there was quite a bit of retrofitting to make that project feasible for the client. And a lot of times, like I stated, this often involves removing large pieces of the structure, reinforcing the concrete, whether that's with new concrete or fiber wrap or with structural steel. And then, like I stated, lifting the structure. Anything that gets lifted will need to be strengthened to support itself during the lift. So lifting itself. Lifting is, I like to break everything down in construction into smaller pieces and smaller projects. So lifting, these are all large items, usually critical lifts due to their weight or due to the fact that you could be lifting over another structure or object. And so all of the structures pose a lifting challenge. As you saw in the previous pictures, the coke drums or coker structures are vertical units. They do not have a landing deck or something where it's simple to sit equipment on. So you can see in the picture there that that is a delta valve that is on the hook of a 500-ton crane. The delta valve itself, just for some information, that there weighs 78,000 pounds. And you can see that it's off-centered. So the center of gravity on the delta valve or any of the devices we install usually isn't in the center of the item. So setting up the rigging, setting up the lift plan is very crucial, not only just to do it safely, but to make it completely successful and to understand how we're transferring the load from the crane to the structure itself. Some of the other challenges posed in revamps are clearances and just the overall space limitations that are in the older or existing structures. You got to remember the structures were not designed to hold or house some of the new equipment that makes the deheading operation safe. So as you can see in the upper left picture there, the arrows pointing to a small gap of light between a delta valve and the bottom flange of the coke drum itself. In that particular instance right there, a lot of engineering, a lot of time went into it with the team making measurements, check twice, cut once, but that gap there was 1 inch between the top of the valve and the bottom of the coke drum. The bottom picture gives you a little bit better view of it, but as I stated, on the old drums or the old structures, space is very limited and everything has to be precise with the engineering and with construction. So just to talk about some of the devices that we install in coke drums, and coker units. The left picture is a bottom unheading device and a center feed device coupled to the bottom cone of a coke drum, just to give you an overview of how it goes together. And then the line feeding the center feed device, which is that shiny piece of pipe there, is the feed line going in. The center picture is the center feed device, and it has two large holes there in the insert, and that is how the product gets fed into the drum, dispersed evenly. And then on the right is a bottom unheading device. So a bottom unheading device, you can think of it as a very large gate valve, and that is what seals the bottom of the coke drum to the chute, which then drops into the containment area for the coke, and that eliminates operations or personnel from harm's way in the deheading of a coke drum. The next one here is a picture of a top unheading device. So as Grant talked about, the drums get filled and then the drums are cut. So cut with hydraulic methods. So the top unheading device is very similar to the bottom unheading device. They're just different in size. So it's still a very large gate valve. But you can see on the piping going above and below the valve there, it is connected to the top of the coke drum. This fully encapsulates the drilling system and drill stem. And this alleviates at the top of the drum for any steam or product or anything or gases coming out. It removes the operational staff from harm's way and captures all of that by encapsulating it and then making the process automated as well. So I'd like to go through some of the highlights on a couple projects that we've completed in the past few years here. So this project, and that's a picture directly from the project, was a 2-drum coker unit. And some of the highlights that we put in: new electrical control systems, 2 new control panels which operated the delta valves and the deheading equipment completely remotely without having any operational people in harm's way. We also added a new SIS system. We had to do extensive modifications to the structure for the structural steel just to support the new equipment. And we had to provide new egress. As I stated, space is very limited on the existing cokers because they're not designed to hold this new safe equipment. So in doing so and adding this equipment, we always have to look at providing new egress and safe paths for any personnel on the structure. So that was one of the big challenges on this project too, was adding the decking and egress for the operational staff. And then different cokers have different ways of moving the product after it's cut and removed from the drum. This particular project had a coke pit, and it has 2 large gantry cranes that move back and forth. And since the equipment is large, it did protrude from the structure. So to make things safe, we did have to add some new stops, modifications to the gantry crane to make sure that that crane did not come in contact with any of our modifications, whether that be the egress decking and or the gearbox for the delta valve. And then we installed 2 new center feed devices for this coker unit, further making the operation safer and removing people from the operational area. This next project was a 4-drum coker, and similar to the first project we showed you there. Some of the highlights: we replaced all the bottom cone sections, so bottom cones all had to be removed due to warpage and deterioration. And then we demolished all of the existing process and utility piping associated with the feed and the deheading. We added 4 new control systems and control panels to making this completely operational from a distance. And then a new SIS system. So I know I touched base on the SIS in the last project, but to give you a little more insight, the SIS system is a very robust system. It has a lot of interlocks, a lot of safety built into it, and making it so there's a set way to dehead, dump, and remove product or add product to the drum. And going through the selling of the system or testing of the system is very intense, to say the least. It's a multiple day operation, and you go step by step through every scenario possible. So it makes, at the end of the day, it makes the deheading and coke removal and coke filling portion extremely safe. And then on this project also, we had to add new decking. And one of the workarounds we did, we added a new deck or expanded that deck, enabling us to maximize our pre-turnaround work and also providing new egress for the operational staff. So coke drum deheading device additions, I've been talking about this, but some more of the challenges and mitigations that we have to, that are posed to us in these structures. So modifications of the cone, as I talked about, removing the cone so that the new deheading devices fit properly and we have enough space. With cone removal or any repairs on the coke drums comes post-weld heat treat. The new equipment that we're installing is very complex, as I talked about with the SIS testing. It goes through rigorous testing and scenarios on the sequence that valves are opened and closed. And then relocation of feed, quench, and steam piping all the utility lines. So nothing is in its same location as in the previous coker structure. All of our upgrades require reroutes of all the piping. And then factory integrated testing of all the devices. As I stated, it's robust testing. And then challenging for rigging in the valves. You can see in that bottom picture there, that is a 78,000 pound valve on the hook of a 500-ton hydraulic crane. And as you can see there, it's not a direct just set the valve in its location. So that is a dance, if you will, of transferring the load from the crane to a rail system and then moving that valve into the actual structure itself. So very complicated. And then we also provide training for all of the operational staff, and that's training on how the entire system works for the SIS system, the controls, and making sure that everyone understands the proper operational path of the new equipment. And at the time, we're currently executing several of these installations right now. We've got a few coker projects around the world that we're working on. And then with that, I'd like to turn things back over to Grant.
Thanks, Kevin. So just going full circle, we started with the safety moment and showed some of the innovations that enhances safety in a delayed coker. The justification for a lot of these projects is often based upon improving uptime, reliability, or just end of life of equipment. But equally important is the fact that this is the most dangerous area of the plant. And anytime you open up any equipment on a daily basis is complicated and dangerous. And all of these upgrades that we've talked about and we've been involved in remove workers from harm's way. There's been a lot of injuries and deaths over the years because of specifically on coke deheading mishaps. It's probably one of the highest at-risk activities in a refinery. So protecting people is absolutely key, and it's more and more becoming an industry requirement, not just to have a deheading device, but also to have the associated SIS systems that Kevin talked about. You know, coke drums wear out. Many operating coke drums are nearing their end of life. It's not realistic that any refiner is going to be able to replace a coke drum without incorporating all of these new safety features, meaning putting in these slide valves and upgrading their SIS systems. So that completes the presentation. I thank all who listened in, and I'm going to throw it back to Maureen now.
All right. Thank you so much, Kevin and Grant. We have a number of questions that have come in and that continue to come in. So I hope you guys are ready. So the first question is about materials selection. So I'm going to send this first to Grant. What are the typical material selection parameters in delayed coking units? Specifically, what are the typical material standards and grades for piping and equipment in such processes? So I realize that's a broad question. That's the way it was entered. So if you wanted to maybe hit some of the highlights, some of the key points that you think are critical, that would be terrific.
Well, I'm not a metallurgist, but what I've seen is a lot of the piping is 9 chrome material, where there's high acid number in some of the crudes that we encounter. They've actually had to increase even from 9 chrome to something more robust on a few projects that we've worked on. 317 stainless comes to mind. The coke drums themselves are, I believe, 1 1/4 or 2 1/4 chrome moly drums that are about 2 inches thick, I recall. Even in the downstream, because of once I've made products and I have heavy gas oil and diesel and material like that at my fractionator, even in my product streams and my pump around streams, there's hot sulfidic corrosion going on. So if I'm over a certain temperature and I have a certain amount of sulfur, those lines typically have been 9 chrome and 5 chrome. So hopefully that answers some of those questions.
I think that's a great answer, right? It's a broad topic. There's a lot of stuff, but I think that hits some of the high points. Okay, here's another question, and this question goes to Kevin. Kevin, how long was the turnaround duration for the drum replacement project, including the derrick removal and reinstallation?
So that project itself was at the 50-day mark. Now you have to preface that with the over 1 year of pre-turnaround activity. So working during the batch cycles in a safe manner, getting everything ready for the outage and making sure that we maximized all the pre-turnaround activity, and then completely scheduling out that outage. Can't say enough about scheduling and planning, but that outage was scheduled down to the hour-by-hour increment in our schedule so that we knew exactly what was happening and when it was happening and why.
All right, great. Thanks, Kevin. Okay, here's another question. I think probably I'll send it to Grant first. Kevin can chime in at the end. Historically, coker systems have been the source of many major fires in facilities. Can you explain why this is and what has been done to reduce the risk of fires from coking operations?
Yeah, I'll address this. So, like I explained, there's always 2 coke drums, and one is in coking mode and one's in decoking mode. When I go into decoking mode, I have to eventually open up that coke drum to the atmosphere, right? So my isolation from the operating hot drum to the cold non-operating drum has to be very good. I have to have the right isolation valves, the right number of isolation valves, and the sequence with which I turn those valves has to be precise. If I don't get a lineup right, then I might be opening up a hot coke drum at 800 degrees, and I might route that material to a coke drum that's already open to atmosphere. That immediately will the material will ignite and cause a fire, right? So these SIS systems that Kevin and I have talked about are very, very crucial and critical to reducing those kinds of mishaps.
Grant, that's a great question. And Kevin, just real quick, I did see something come through the Q&A. Can you define SIS, Grant? I don't know that it was defined earlier, and one of our listeners has asked.
SIS is safety instrumented systems. So it uses a lot of instrumentation. The instrumentation will tell you something about temperature or pressure or flow or something, and then it's a dedicated system that basically looks at these components and says, you have to do something, or you have to not do something, or you can't do something. If I'm at temperature and pressure, it won't allow me to open up maybe a valve that you think you want to open, but it's telling you, no, no, no. It would not be safe to open up this system. So it's not your normal PCS, DCS operations of measuring flow and modulating a control valve.
Thanks, Grant. Kevin, did you have something to add?
No, I mean, Grant covered that quite well. The SIS systems have a significant amount of permissives that only allow certain valves and certain things to happen while other things are closed or not happening. And then just to further on to the question, I know, Maureen, they asked about some of the things we've done. A lot of the new, even though we're putting in new devices and making the structure much safer, one of the large things is egress and making sure that in the event of any type of failure or problem in the structure, that the operational staff can leave the area. In the older structures, that was not there. It just wasn't there. They didn't, there might have been one stairway or a ladder at the corner of the structure. And one of the things we go in and do is provide that new egress and that new path of safety. We also put in new deluge systems. I know I didn't mention that, new fire suppression and deluge systems throughout the structure. Even though we put in the delta valves or the deheading devices and sealing everything off, we still add new safety systems to the structure itself, just as as added precaution.
All right, I actually have another question here related to fires. Are drum cracks also a source of fire in coker units?
I mean, I suppose they could be. I haven't come across that with proper, inspection. We should be catching that stuff, or the owners should be catching that stuff. I don't recall ever hearing about a fire from a cracked coke drum.
So yes, it is. I've unfortunately worked a lot of outages, and several of them in cokers. The drum cracking or drum bulging is what produces the cracks over its cyclic condition. And a lot of times the drums are run past their life expectancy, and as the drum cycles in and out, obviously it's hot, cold, the drum starts to shrink, causing these bulges, and then the bulges will eventually crack. And as you've seen from the pictures, the drums are all completely insulated. So yes, they do have inspection and maintenance. It's quite rigorous, especially nowadays. In the past, it wasn't as rigorous, and there were fires due to breaches and cracks on the drums themselves.
All right, great. Okay, so let's go on to a new line of questioning. Kevin, one of the projects you mentioned, the replacement of the cone. Was that done in place, or was the drum removed?
That project, we did that in place. So from the skirt up, or in that project, the drum was attached just above the tangent of the vessel to the skirt. That portion stayed in place. We removed the cone section of each of all four of those drums, and then replaced it with new cone sections to be able to give us the room to mate to the new deheading devices. And as we were talking about material before, that was 1¼ chrome half moly cones lined with 410 stainless, which we fabricated those and had them brought in.
All right, terrific. Wow, the questions keep flying in faster than you can answer them. Okay, here's another one. What is the best location for the deheading panel and equipment? And are there specific requirements around this?
So I'll start, and then Grant, you can jump in. On most of the cokers, the operational staff likes to have the control panel at the operational shelter itself. So the operations staff is completely removed. I've done it that way. We've done it in a remote location or on a deck that is adjacent to or behind and above the deheading location, so that operational staff still has a line of sight to the deheading devices. I know we didn't show exact schematics of a deheading device, but usually there's a stem portion that's moving and there's a flag attached to that stem, and you can see that at a distance. You can see that flag move in and out, and that's indication of the gate actually sliding open and close. So to answer the question, you can have a control panel to operate the CFD and the deheading device within vision or line of sight to it, or you can have it at a remote location. And honestly, that has just been on the determination of the client. There are no specific rules about how far away the control panel needs to be from the actual deheading device.
Yeah, that sounds about right. I've worked with an owner that wanted to be able to do everything from the control room. At the start, they needed operations to go out and do exactly as you say, Kevin. They need to go flag that is this actuator moving? Did this valve actually move on demand? And once they got comfortable with doing that, they were fully with the idea that they were going to do everything from the control room.
And one of the systems we've set up too is with the control room portion, we've also put in CCTV cameras so that the operational staff can see on a monitor in their control room. It's actually pointed at the flag and at the stem so that they can actually see that flag from a remote location moving, and they don't actually have to have anybody on the cutting deck itself.
All right. Great answers, you guys. Here's another one. I'm going to direct this one to Grant. There's a few acronyms in here, so I'll ask you to define them as you're answering, please. What is the typical sill level for the SIS systems used on these deheading devices?
I am not entirely sure. They might have to be sill 3. I don't know. They might be able to get away with sill 2 depending upon, once you run the LOPA and you find out your levels of protection and the backup systems that you have. But I do not recall whether they're sill 2 or sill 3.
All right. Thank you. And I guess to the audience, we'll look that up and we'll include it in the Q&A that we send out at the end. Here's another question for Kevin. On the reliability project, the first one that you mentioned, how long did it take to build the crane pad and erect the crane?
So the crane came in on approximately 70 semi-truckloads of equipment, and that was a 6-week process to erect the crane itself and to test the crane. The pad itself, we had to pour a special pad. We drove piles and made sure that that was a safe location because, one, the crane was extremely heavy, and number two, the lift that we were picking was also heavy. So from beginning to end there, I believe it was a 4-week to 6-week period for the pad itself, and then another 6 weeks once the pieces parts started coming in for the crane and being able to erect it and have it tested and ready to move.
Okay, thank you, Kevin. I have another question, and I know Grant sort of is more of the greenfield, brand new facilities, and Kevin, you're the revamp. But I think this might. I'm not sure who this is going to be for, but on a cone replacement, do you know the type of stress analysis that was done for that drum? And once again, if we don't know, we can confirm with the mechanical engineer and advise in the written Q&A.
So on the cone replacement, we did a finite on specifically the project that we talked about. We did finite element analysis. We also brought in a group of machinists, and we tracked the movement of the cone section through its cycles and multiple cycles just to verify the amount of movement. And those drums actually moved approximately 2.5 inches in any direction, and that was determined based on, because it was a side feed for those drums. But so we go through and went through a significant amount of pre-engineering work just to find out how much the cone moved, where exactly to cut the cone, because we were trying to obviously replace areas that had been stressed significantly. And then another portion to that is, I know we didn't go into detail on the delta valve systems, but they are also supported by spring cans or a suspension system. And so we had to calculate in the amount of movement that would be in the spring cans to track the cone systems to make sure that we didn't bind anything, because the drum or the delta valves do need to sit in a neutral state when they're attached to the drum.
Sounds like a lot of work.
Yes.
All right. All right. So here's another question. I think it's probably for Grant. With a top unheading device, how does the cutter enter the drum?
Okay, so first off, we have to say that there is a top unheading device. I must be able to open up the top of that drum. So if you're putting a slide valve on the top of the drum, really the gate or the disc just slides off to the side laterally, and I have now an open hole. So the drill stem is attached to a hose, and the hose doesn't really reel up because the pressure in the hose is 4,000 psi, and so the hose is very, very thick and has to be rigid. And that's why there's derrick structures 120 feet above the coke drums, because the hose just goes up and down instead of being reeled up. So the drill stem is attached to the end of that hose, and it's just dropped down inside the coke drum. There's permissives on that system as well to ensure that the drill stem is actually inside the drum before they start water to the drilling device.
All right, very good. I have another question. If you were to design a new facility, what are the minimum clearances around the equipment that you would consider to enable easier access for maintenance and replacement in the future?
I can't answer that. We have setback rules, we have area classification rules, we have all kinds of rules about spacing of equipment. The last coker I built, I was actually, too often I don't get to go out to the field and see my handiwork, but the last one I went out there and I was amazed at how much space there actually was. The rack was very wide. The spacing of equipment was, there was space to go in there and drive a truck through and do anything you wanted to do. I will say on a project recently, we put a bunch of steam purges to a bunch of valves to clean them, because there's always coke fines in valves. And they had all these little 3/4 inch valves on all these valves, and it restricted egress in a certain area, right? So I guess we didn't see that in the model. We didn't realize really what was going on with the 3/4 inch piping, because we don't model that a lot of times. And we ended up taking out all of that piping, and we just said, we're just going to have to operate these. In fact, it wasn't our decision, it was the client decision. They said, rip it all out. We'll operate these valves. Don't worry about it. But there are setback rules depending upon the type of equipment, and restrictions. I don't know exactly what all those are. There's so many of them.
So I'll jump in a little bit, Grant, on that one too, working in operating units and doing shutdowns. One, if you were building a grassroots coker and you're utilizing deheading devices, one of the things would be on the top of the structure to have plenty of room for maintenance and repair of the top unheading device, being able to remove it from the drum itself and setting it off to the side, and whether you're replacing seats or replacing a gate or just general maintenance. Same would go for the bottom deheading device. So one of the things we did on a revamp project, it was a bottom supported delta valve. We extended the support rails far enough out to where the valve can be rolled out of the way, and they could actually do seat replacements on the deck instead of picking that valve up, going through that extensive process of getting a very large crane and going through the entire critical lift program and putting that valve on the ground and doing its maintenance there. On that specific project, we made it to where they can do some maintenance of the valve on the deck without removing it. If you're building a brand new one, I would make it so that there's plenty of deck space and the deck is supported sufficiently so that you can do maintenance of that equipment on the deck and not have to take the step and bring the people in to remove it via crane and lift plans and such.
Okay, well, I think I got through about 10 questions, and I see 43 in the Q&A. So I think that you're going to have some homework, Kevin and Grant. But I want to thank both of you for taking the time to talk with us today about some of the innovations and some of the experience that Fluor has had recently with delayed cokers. And I want to thank the audience for dialing in and attending today. There's been a great deal of engagement, and it's been a pleasure being your moderator. We will be hosting our next webinar on Thursday, October 22nd at 10 a.m. Central. And Fluor's subject matter experts, Eddie Guidry and Carlos Martinez, will be giving a comprehensive discussion of important considerations and some of the common design challenges that you face when engineering totally enclosed fan-cooled electric motors that are required to be located in Class 1, Division 2 hazardous classified locations. This is specifically relative to the hot surfaces of the motors. I've heard the dry runs, and there's a lot more to this topic than I ever realized. So please keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for future webinars. We appreciate your attention, and thank you again for dialing in today. We will send a compiled list of the Q&As out within a few days, along with the notification that the webinar recording is available for replay on fluor.com. If you have any additional questions or require more information, please email innovation.builders@fluor.com, and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.